Hey guys, in this video, we're going to introduce the second derivative and how it applies to certain notions in physics, such as position, velocity, and acceleration. And this is going to be from Chapter 2, Section 5 in the textbook. Okay, so in the last video, well, a couple of videos ago, we talked about how derivatives can be graphed because derivatives are just functions. So we can take the derivative of a function. We can also take the derivative of a derivative. Because the derivative of the function, we can take the derivative of it. And this is called the second derivative. And we usually denote it like this with 2 primes. So this is f double prime of x. This is our second derivative. And so this first example says, find the second derivative of f of x equals x squared. So next week, we're going to talk about a shortcut to finding the derivative. But for now, we're going to use the limit definition. So the limit definition says the limit as h goes to 0 of f of x plus h minus f of x all over h. Okay, so let's go ahead and do this. Now, if I put in x plus h into x squared, I get x plus h squared minus x squared all over h. And I can FOIL the top. I can FOIL this guy right here. That's going to give me x squared plus 2xh plus h squared minus x squared over h. These guys cancel out, and I can factor out an h. Factor out an h, 2x plus h over h. These guys can cancel, and I'm left with 2x. Okay, so this was f prime of x. This is my first derivative, and to find my second derivative, f double prime, I can just take 2x and put it back into that limit function for f of x. Okay, so let's do the second derivative. We have f of x plus h. This time I'm plugging in x plus h into that guy. So this is going to be 2 times x plus h minus our original function, which is our derivative, all over h. All right, so these guys cancel, the h's cancel, and I'm just left with 2. So this is going to be my f double prime of x. It's my second derivative. Okay, so the first derivative of x squared was 2x. The second derivative is just plain old 2. So let's go ahead and look at these functions, the graphs of these functions. So last time we talked about the relationship between a function and its derivative with respect to the graphs, and we can see the same relationship between a derivative and a second derivative. They have the same kind of relationship. So remember, when the slope of the tangent line of the function is negative, then let's see. So if we look at our original function in red, the slope is negative right here. And so that's telling us that our derivative function should be below the x-axis on this interval. And we see that that's the case, right? Our derivative, our first derivative is 2x, and we can see that it's going to be below the x-axis right here. Okay, so this is where this is coming from. So, and right here, the tangent line to this little flat spot is the slope's going to be 0, and so we should expect the derivative function to cross right there. And now on this side, the derivative function, we can see that if we draw a tangent line to any point on the right side of this curve, then the slope is going to be positive. And since that's the case, the derivative function should be above the x-axis on this side. And that is the case, as we can see. So the first derivative is 2x, and we can see that it's a straight line from the picture. So we can figure out what the slope is of this line, and we can see that it's just 2, right? The slope is 2, rise over run. So we rise 4, run 2, so our slope is 2, and, so that occurs at every single point, right? The slope is always going to be the same on a line between any 2 points. And so that's telling me that the derivative is going to be a constant function graphed at y equals 2, as we can see right here. Now, the second derivative is always positive, and that makes sense because the first derivative is constantly increasing, right? So that is one way to look at these derivatives and second derivatives with graphs. All right, so recall that last time we talked about if a derivative is positive on an interval, then the function's increasing over that interval. If the derivative is negative on the interval, meaning it's below the x-axis, then the function is decreasing over that interval. And so in a similar way, for the exact same logic, the second derivative, if it's positive on an interval, the first derivative is increasing. If the second derivative is negative, then the first derivative is decreasing over that interval. Okay, so same exact logic as before. And, we can see that here with our 3 functions. And we talked about that, on the last slide a little bit. But let's see, where is our second derivative negative? It's not negative anywhere. And so that tells us that my first derivative is never decreasing, right? My first derivative is this guy, right? And it's always increasing, right? As x gets bigger, y gets bigger. That's what increasing means. Whereas, with the first derivative, it is negative right on this interval, which tells us that our original function is decreasing on that interval. When x gets bigger, y gets smaller on this interval. However, when on this interval, f prime is bigger than 0, right? We have this guy is positive, and so that's telling us that my original function is increasing as x gets bigger, y gets bigger. All right, so now let's talk about the shape of the second derivative. If the second derivative is positive on an interval, then the first derivative is increasing. We just talked about that. And therefore, the graph of the original function is concave up, which means it's like this U-shaped right here. If the second derivative is negative on an interval, then the derivative is decreasing, so the graph of the original function is concave down there. And so that's going to be this upside down U, concave down. Now, if the second derivative is 0 at a certain point, then at that point, that's going to be a point of inflection. And what that means is that at that point, we're changing from concave up to concave down or vice versa. So let's take a look at these graphs that we have. Okay, so let's go ahead and analyze these graphs. So again, the red graph is going to be just the regular function, f of x. The blue graph is the first derivative, and the green graph is going to be the graph of the second derivative. So the first thing that I like to do is kind of look at the points of inflection. And so remember that the points of inflection occur when the second derivative is equal to 0. In other words, where does it cross the x-axis? And that happens right here and right here. So if we look down at our red function, that's telling us that the points of inflection are going to be right here, where it changes from concave down to concave up to concave down, and also right here. And it looks like it's changing from concave down to concave up right there. Okay, so those are the points of inflection on our red function. And also notice that, it says if the second derivative is positive on an interval, then the graph is concave up on that interval. And we can confirm that, right? Because right here, so this is our first x value all the way here, the graph of f of x should be concave up. And indeed, it does look to be that way because this is sort of a flattened U shape. Okay, so it's concave up there because it's positive. It's also going to be concave up right here. All right, so it's going to be concave up right here, which also agrees with our picture. Now, wherever the second derivative is negative, the graph should be concave down. And we can see that it's negative when it's below the x-axis. And so this whole portion right here, this whole portion right here is going to be negative, and therefore the graph of f of x should be concave down on that interval. And we do see that this is the case. All right, it's concave down right there. All right, so let's do some examples. For the functions graphed, what can be said about the sign of the second derivative? So we have three functions graphed, and we're trying to figure out, the concavity, basically, to determine the sign of the second derivative. So if we look at A, this thing is concave up all the way, right? It doesn't ever concave down. And so what this tells us is that the second derivative is always going to be positive. Okay. Now let's look at B. So B, this thing, it's not exactly a straight line. It's a little bit flat. And so we can deduce from this that this thing is concave down, right? It's like a flattened upside down U shape. And it appears to be concave down throughout, negative infinity to positive infinity. And so that tells us that the second derivative of this function, and actually I should name this g double prime of x is going to be negative for any x. All right. Now let's look at part C. So part C, this one's a little interesting because I see a point of inflection. Where does it go from concave up to concave down? Right here in the origin. So that's my point of inflection right here. And it looks like it's concave down right here, right? Because that's kind of a part of, an upside down U, concave down. And then it looks to be concave up on the right side of 0, right here. And so what this is telling us is that, maybe we could say it like this. Maybe we could say from x. And by the way, you might see this little symbol in your homework. This means is contained in. So if x is in the interval negative infinity all the way up to 0, then that tells us that h double prime of x, our second derivative, is going to be negative. All right? So from negative infinity to 0, the second derivative is going to be negative. On the other hand, and maybe we should use better grammar and say when. So on the other hand, when x is in the interval 0 to positive infinity, our second derivative is going to be positive because that thing's concave up. All right, so part C was the only one where we had different signs of the second derivative for different portions of the graph. Okay. Let's look at this example. In the figure below, what are the signs of the second derivative? What are the signs of the first derivative at each point, assuming? So let's look at point A. All right, so assuming this red curve is f of x, just our regular function. So remember, let's actually look at the first derivative first. So we're looking at f prime of x. Well, if this is f of x, remember f prime of x, the sign of that is going to depend on the slope of the line tangent to a. And if we, kind of sketch out that line, we can see that it's a negative slope. And so the sign for f prime of x is going to be negative. What about f double prime of x? Well, again, at point A, for the second derivative, we're concerned whether it's concave up or concave down. And it looks like this is part of a regular upright U shape. So that's concave up. And since that's the case, this thing is going to be positive at A. All right, let's look at part B. So it appears that B is on that flat top of the curve. And remember, at any flat point, the line tangent to that point is going to have a slope of 0 because it's horizontal. Okay, so our slope here is 0, and that means the sign of f prime of x at that particular point is going to be 0. Oops, let's get this back. Okay. All right, what about f double prime of x? Well, this is at the peak of an upside down U, right? So it's concave down. So that means that at that exact point, the sign of the second derivative is going to be negative because it's concave down. What about C? Well, this is it looks like C is an inflection point. I'm just going to guess that C is an inflection point because it looks like it's going from concave down right here to concave up right here. And so I'm going to say C is an inflection point. And what that means for, I guess I did this one backwards, but what that means for the second derivative is that its sign is going to be 0 right there because it's going from concave down to concave up. On the other hand, the first derivative, well, if we were to draw a line tangent to this point C, that's going to have a negative slope. So the sign of this guy is going to be negative. All right, let's look at our final one on here, which is D. So for the first derivative, if we draw a tangent line, the slope is positive, and so the first derivative is going to have a positive sign at that point, D. What about the second derivative? Well, it appears that D is part of an right side up U, concave up, and so this thing is going to have a positive sign as well there. Okay, so you're going to see some examples like this in your homework. It says select the correct sketch of the second derivative of the function of f of x shown below. So the way that I do these is just by process of elimination. And so we're given f of x to the left, and we want to figure out what the second derivative looks like. And so what we're kind of after is where does it concave up, concave down. So if I look at this graph of f of x, it appears that it's concave down right here. And maybe this is a point of inflection. That kind of looks to be the case. And it's also concave down, probably right here. And then it starts to flatten out. And then it's going to be concave up right in this little interval. So let's go ahead and go through these things and use the process of elimination. So, okay, it tells us the leftmost value, it looks like from approximately x is -3 to x is -1, f double prime of x should lie below the x-axis because it's concave down. So let's see. We can automatically eliminate this one because, look, from -3 to about -1, it's above the x-axis, which shouldn't be the case. It should be below. Okay, let's look at choice B, which is this guy. Well, it looks like, let's see. Yeah, it looks like this one might be okay on the left side, right? Because at -3, it looks like it's below the x-axis all the way up to -1. And we said that that was the inflection point, which agrees with our picture. And then it starts to go up, and it should be above the x-axis up until 1, and then it should dip below. But we can see that that's not the case. Here's x equals 1, right? And it should be above, which is good. It's above the x-axis there. However, because of this portion, right, from about 1 to 3-ish, it's not below the x-axis for that whole portion, right? It's above the x-axis right here. And so for that reason, we can eliminate that guy. Now let's look at this guy. All right, so we are below the x-axis up until 1. That looks good. And we should be above the x-axis up until about +1, and then it should dip below, but it doesn't. So again, that can't be correct. This guy, though, does agree with everything we said. So from about -3 to -1, it's below the x-axis. That's good. From -1 to +1, it's above the x-axis. That's good. And then from a little more than +1 up to +3, it's below the x-axis. So this is our match right here. Yay. Okay. Okay, so we want to graph the second derivative of the function in red. So the first thing that we can do is we can just graph the first derivative, and from the first derivative, we can graph the second derivative. Okay, so let's go ahead and look at this. So we want to look at where the tangent lines have a positive, negative, and 0 slope to the original curve. So we can see that that the slope is negative on this interval. It looks like from x equals -infinity to x equals -1. And then it looks like we're going to have a 0 slope right here, right, where that horizontal line touches the vertex. And then to the right side of the vertex, we are going to have a positive slope. So what does that tell me about my derivative? Well, that tells me that my derivative is going to start below the x-axis, and it should go through the x-axis right here, where the slope is 0. So it's going to be below the x-axis, and then it's going to just start climbing above the x-axis. All right, so this is going to be f prime of x. And so for f double prime of x, we're going to just apply the same logic that we used to find the first derivative graph. But this time we're going to use the derivative, f prime of x, and look at the slope there. So it looks like the slope of this line is roughly 3, right? And remember, with lines, the slope is always going to be the same no matter what 2 points on the line you choose. And so for that reason, we are going to have a slope of 3, and so that's going to correspond to this horizontal line right here. So this green is going to be our f double prime of x. Okay, let's do another example. So again, I'm going to start by graphing the first derivative. And I can see where it's flat, right here and right here. And so that tells me that my first derivative is going to cross the x-axis at these x values. So I'm just going to go ahead and transfer these down to the x-axis. All right. Now, to the left of that first orange point, we can see that the slope is constantly increasing. And so that tells me that this thing is going to start above the x-axis. So maybe something like that. And then it starts decreasing up until we get to that next orange point. So maybe it's going to go below the x-axis like this. Let's see. Okay, and then it's going to start increasing again on this interval. Alright, let's trace this out, maybe in, which color did I use? Purple for f prime of x. So let's go ahead and trace that out. Alright, so this, what I'm tracing out in purple is our f prime of x. Now for f double prime of x, again, we're going to look at where there's flat portions on f prime of x first. And it looks like the vertex of this is going to be right about here. So I can transfer that up to the x-axis. And then to the left of that, the slope is going to be negative, 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 all the way until it gets to that orange point. And so that's going to tell me that this thing is going to start below the x-axis, and then it starts to, the function starts increasing, so the slope becomes more and more positive, and so that tells me that this thing is going to continue up like this. And so it kind of looks like a straight line here. Maybe I'll trace this out in yellow. So it should look something like this. This is our f double prime of x in yellow. All right, so now we're going to talk about position, velocity, and acceleration. And I sort of alluded to this a couple of videos back, but I want to get more into it, and we're going to go even deeper into this in later sections. But, okay, so what is position? Well, a position graph basically tells you where you are at some moment in time. So we can talk about height as position, or we can talk about horizontal distance as position. Okay, and so the velocity curve on the y-axis is velocity, and on the x-axis is time. Okay, so velocity is basically speed with direction. So, you know, if you're backing up your car at 20 miles per hour, well, you probably wouldn't tell someone I'm going negative 20 miles per hour, right? You would tell them I'm going 20 miles per hour, because when we usually, in everyday speech, we talk about speed, but velocity has direction. So if I'm going forward, if I'm moving forward in direction, whatever forward means, that's going to have positive velocity. But if I'm moving backwards, it's going to have negative velocity. So if I'm just driving my car on the interstate at 60 miles per hour, then I have positive velocity because I'm going forward. So that's going to be positive 60 miles per hour. And if I'm going backwards, if I'm going in reverse 60 miles an hour, then that's negative velocity. Okay, so that's the distinction there. And so we're going to talk about the relationship between these curves. And then acceleration, is basically how fast your velocity is changing. So what is the relationship? Well, velocity is the derivative of position, and acceleration is the derivative of velocity. Okay, so, and I mean, if you think about it, it makes sense, right, with the units, because let's say that we have this position curve as shown right here, And we have 2 points on this position curve. So this is describing, my position at some time, right? At 2 times. And so when we talk about derivatives, we talk about slope, right? And so think about it. What are the units of the slope of this? If this is the average position. Well, the units, are y values in meters, right? So the change in, slope is the change in y over the change in x. And our y is in meters where our x is in seconds, right? So distance over time is our slope. And we can see that this makes sense because our units of velocity are in meters per second, all right? So anyway, let's go ahead and get into this. All right. So if I am given this position curve and I want to graph its derivative, I would just do what we've usually been doing. I would just look at the slopes and look for the flat areas. So it looks like we have positive slope up until that orange area, then we have negative, and we have 0 slope again, and then we have a positive slope here. So I can take this and sort of graph a rough sketch of the velocity function. I see that at approximately right here, it should cross the 0 axis, and maybe right here as well. Okay, and then it's going to be above. It's going to be above the curve until we get here. Then it's going to dip below. And then it's going to come back up. And so maybe it looks something like that. All right, so velocity is derivative of position. Now acceleration is the derivative of velocity. So we need to look at the velocity curve and sketch the acceleration curve based on that. Okay, so it looks like it's flat right here at the vertex, and so that's telling me it's going to cross the x-axis approximately right here. Now the slope of this velocity is going to be negative until it gets to the vertex. So this thing's going to actually start below the x-axis. It's going to cross that vertex and then it's going to come up. So maybe it looks something like that. So yeah, acceleration is the second derivative of position. Very important. We're going to come back to this idea time and time again. Okay. All right, given the position function, h of t equals negative 2t squared plus 3t, find the velocity function and the acceleration function. Okay, so we're going to have to take derivatives, right? So I'm going to, you guys are going to get super mad at me, but next week we're going to do a shortcut on finding derivatives, but for now we're just going to use the limit definition. Our good friend, this guy. Now, okay, our independent variable is t, so I'm actually going to replace x with t just so that we stay consistent here. And I guess technically it's h, but whatever, I'm not going to change that. All right, so now I'm going to plug in t plus h into my variable t. And so this is going to give me negative 2 times t plus h squared plus 3 times t plus h. And then minus f of t, which is just negative 2t squared plus 3t. That's going to all be over h. And then I can start doing the algebra. So t plus h squared, I'm going to just do this off to the side. Let's see what this is. Okay, so let's carry that down. We get negative 2 times t squared plus 2th plus h squared plus 3t plus 3h. Oh, shoot, I'm running out of room. Plus 2t squared minus 3t. And that's all over h. And I'm being a little sloppy, but again, we're taking the limit as h goes to 0. Okay. All right, so I'm going to distribute that guy, and we get negative 2t squared minus 4. Let's write this a little bit better. Negative 2 t squared minus 4th minus 2h squared. All right, and then I'm going to be able to cancel out some things. Let's see. So if these guys I can cancel. These guys can cancel. And that's about it. So now I'm going to factor out an h. Okay. All right, and my last step is to plug in 0 for h. Okay, so here's my answer. So what did I just find? Well, I took the derivative of the position function. So I found v of t. This is the velocity function. And so I can figure out what the velocity is at any instant in time with this function. If I plug in t equals 1, that tells me that the velocity is negative 1. And what's our units? Negative 1. Well, I didn't give units, but let's just say meters per second. So that means that that thing is traveling 1 meter per second in the negative direction when the time is equal to 1 second. So we can do the same thing if we want to find the acceleration. We take the derivative of the velocity function. And so, again, we're using our derivative definition. So we have negative 4. This is f of t plus h minus f of t, all divided by h. Combine like terms and simplify. These guys can cancel, these guys cancel, the h's cancel, and I'm just left with negative 4. All right, so a of t, my acceleration function, is negative 4. What does that mean? Well, that means that the velocity is changing at a uniform rate, right? It's a line. It's a straight line. And since that's the case, the acceleration is negative 4. So the acceleration isn't changing. It's just always going to be negative 4 meters per second squared. All right, so this is kind of important. And, again, we're going to get more into velocity and acceleration once I teach you guys the shortcut. But for now, let's just talk about acceleration velocity and what that means in terms of speeding up and slowing down. So slowing down is if you have opposite signs. If you have negative acceleration, positive velocity, or negative velocity and positive acceleration, that means you're slowing down. If you're speeding up, your signs are the same. So positive acceleration, positive velocity, or negative acceleration, negative velocity. Because remember that the negative just means, the negative doesn't, mean anything about how fast you're going. It just tells us the direction that we're going in. Let's look at these examples. Graphs of the velocity functions of two particles are shown. Particles, just objects, whatever they could, I don't know. Baseballs, grapes, I don't know, particles. Where t is measured in seconds. When is each particle speeding up? When is it slowing down? Explain. So here we have velocity functions, and remember we just saw that speeding up means that the velocity is positive, acceleration is positive, or the velocity is negative and the acceleration is also negative. So that's speeding up. And then slowing down, we have opposite signs. So since we're given the velocity graph, we know where the velocity is positive. So let's look at that first. The velocity is positive above the x-axis. Right, because this is the velocity graph. So the velocity is positive. Where is it positive? It's positive from x equals 0 to about x equals 1.5, it looks like. And where's the velocity negative? Well, the velocity is going to be negative below the x-axis, so it looks like from 1.5 to about 2. All right, now let's talk about acceleration. So remember, acceleration is the derivative of velocity, and so we're looking at the tangent lines to the velocity graph. So acceleration is going to be positive right here, and that's about it. Right here it looks like it's going to be 0. And right here it looks like it's negative. Okay, so where's acceleration positive? It looks like it's positive from 0 to about 1. And it looks like it's negative from 1 to about 2. Okay. All right, so let's talk about speeding up for this first graph. So speeding up is when both velocity and acceleration are either both positive or both negative. Okay. So the velocity is positive from 0 to 1.5 and acceleration is positive from 0 to 1. And so we want to just take the overlap of these, which is 0 to 1, right? Because the 1.5 isn't included in the acceleration part. So it's speeding up from x equals 0 to x equals 1. And it's also speeding up from, well, velocity is negative from 1.5 to 2, and acceleration is negative from 1 to 2. So we take the overlap of these guys, and that's just 1.5 to 2. So 1.5 to 2. So that's where it's speeding up. Now slowing down, we have opposite signs. So let's do that. All right, so velocity positive, acceleration negative. Let's look at these first. Where do they overlap? Well, they overlap from 1 to 1.5. You know, if you were to like graph these on the number line, 0 to 1.5, and then 1 to 2. So then we have so it's going to be overlapping from 1 to 1.5. Okay, what about velocity negative, acceleration positive? Where do these guys overlap? it looks like they overlap from, well, it looks like they don't overlap actually, right? Because if we were to draw these on the number line, 0 to 1 is right there, and then 1.5 to 2 is right here. So they don't overlap. So this is going to be our only interval of slowing down from 1 to 1.5.